Right, as I promised, here's our circuit. It's our simple circuit. I don't know if you can see, it might actually, you know what, I'm gonna just change one of these wires out to make it a little bit more obvious using two different color wires so we can see. I've got a red wire that's gonna be attached to the positive of the battery. I'm gonna connect that to one end of the resistor, the light bulb, and there we go. And then from the other end back to the negative of the battery. Boom. So here's my device. That is my digital voltmeter. It's also my digital ammeter, so I can flip this over here and now it would read current, but we're gonna read voltage here just to show that to you. So you can see the reading there. So if I wanted to measure the potential gain at the battery, I would take the two leads of my voltmeter and I would put one before the battery, so say on the negative terminal, and one after. You can see the reading. There we go. Oh, I got a negative actually, so let me flip-flop the leads there. Okay. Oh God. My contacts are a little loose there. Okay, there we go. Oh, that's just like jumping all over the place. All right, fairly stable there. 4.05 or so. The reason why it's going is I think this lead is a little bit rusted, so my contact is not good. If I come over here now to my my battery or my bulb, get a good contact there. Ooh, geez. You can see that the potential drop is approximately the same. Cool. I must have screwed something up there. There we go. So that's what I was talking about there with Kirchhoff's loop rule. Potential gain by the battery is equal to the potential drop here at the light bulb. And even though the wires were using some of that energy, not very much, which is why we had the same two readings on both. I'm not going to show this as the ammeter because it's just very difficult with this field of vision in order to do that. But I just wanted to show you that one thing work there. Now, what I want to talk about today is what happens when I have multiple resistors. We're going to keep it nice and simple with just two resistors in a circuit, and because it can get a little bit more complicated once you have more than two, but we'll see how it extrapolates outwards. So if I had two light bulbs, boom, and one battery, boom, and I wanted to make a circuit out of them, how would I do that? How could I create connections that would work such that both light bulbs would light up simultaneously? Well, one way I can do that, so actually stop the video for a second and try and sketch out two circuits where both of them, where each circuit would have both light bulbs light up, but it would look a little bit different. So just stop the video and try. All right, so hopefully the first one you got looks something like this. So I would start at, say, the negative of the battery, and then I would go to one of the two resistors. Let's see this one here. All right, cool. And then from that resistor, rather than go back to the battery and make a simple circuit, I would go to the next resistor. So far I've got from the battery to this first resistor, I know it's called 2, but whatever. And then from 2, get to the second resistor, and then from the second resistor, we're gonna go back to the battery. There we go. And there you go. I have both light bulbs on, right? So let's just talk about this particular circuit for a second. So hopefully you came up with that one. What's the defining feature? Hopefully what you figured out the defining feature is that I have one pathway around which the charge can flow. So watch what happens here if I unscrew one of the light bulbs. The other goes out. Why? The reason is because I don't have a closed circuit, right? If I pull this one out, boom. If anything in one of the circuits goes, everything goes, right? These two bulbs, or actually all these elements, are dependent on one another. And we're going to call that a series circuit. So let's just put the demo equipment over to the side here. We're going to do that first. So here we go, a series circuit. And a series, I'm going to have two columns here, folks. A series circuit, the defining feature is that there is one pathway for charge to flow. Okay? And the next thing that we're going to say then about that one pathway for charge to flow, each element is dependent on all other elements. And what does that look like? Well, that might look like the following here. If I have a battery, positive, negative, excuse me, boom, and boom. Okay, and that would be my delta VT, and here would be my R1 and my R2. It doesn't matter which one's 1 and 2, but it comes to the current from the battery, or the current going around is going to go to this resistor and this one back to the battery, right? So there we go, series circuit, boom. Now, a couple of things about the series circuit. Let's talk about Kirchhoff's junction rule. That says the current into something is equal to the current out of something. So here's the current into the battery, which we called IT, and the current out of the battery, which we would call IT, of course, because current through the battery is called IT. But how much current gets to the first resistor? Oh, well, there's only one pathway, so whatever current goes through IT, that same number of charges has to flow this one and flow through this one. So we get that IT here would be equal I1 would equal I2, and if there were 3 resistors or 4 resistors, etc., equals I sub n. Or another way to write that is 2 elements in series always receive the same current. Not only, by the way, the same amount of current, but literally the same electrons. And that's super important. But what about energy? Well, let's use the loop rule. Voltage gains are equal to voltage drops. So here, a charge would come through and gain a certain amount of energy, and then it would travel around. Remember, we're pretending our wires don't have resistance, and it would drop off some of the energy and then drop off the rest. Okay? So gain, drop, drop, gain, drop, drop. Oh, okay. Well, if energy is going to be conserved then by the loop rule, let me divide this in half as well, then we would say the energy or the potential gained at the battery, delta VT, would equal the sum of the potentials dropped at the resistors. And if there were more than 2 resistors plus ... delta Vn, right? Another way to say that is elements in series split voltage. Now, the question becomes then, well, how does it split? Now, you'll notice that my 2 light bulbs before were fairly equally bright, but that's because they were identical resistors. I want to go back to my analogy with the post office, right? So our current is a stream of mail people, right? Each picks up a certain amount of mail, they drop off mail. So here, is it just that like the first house they go to, they just drop off a lot of mail because they don't want to carry a lot? No, they get fired if that's what it was. If they have multiple houses on their route that they're different sizes, I think it's probably reasonable to suggest that a bigger house might have more people at it. And therefore, like if one's an apartment building and one's a single family house, the apartment building is going to get more mail than the single family house. It's the same thing here, because what we can do here, folks, is actually look at Ohm's law as it relates to the individual resistors. The potential drop across resistor 1 would equal the current through resistor 1 times the resistance of resistor 1, right? And delta V2 would equal to I2 R2. But notice here that those two are equal because in a series circuit, everyone gets the same amount of current, and therefore larger R values get a larger share of the voltage. Another analogy, you could also think of like the supplied voltage is like pizza being supplied, right? It's a large pie, it's a small pie. That's set up by the size of the battery. And the resistors are the number of people who have to share the pie, right? If I have 2 people sharing the pie, everyone gets a certain amount. Now, they may not get half each, right? Like maybe one's a big kid and one is a small person. And so, like, I don't know, I won't actually go into the analogies. But like, if 2 people are sharing, you might not get an equal share based on the size of the people. But one thing would certainly be true is that if I added a 3rd person sharing that same pie, everyone would get less. Now, the one that was getting nothing would get something, obviously, but the ones who were getting something would get less. And every time I add resistors or add people, therefore everyone gets a smaller share. So here, adding resistors means that each resistor gets a smaller share of delta VT, okay? So there you go. Now, the other thing that we have to think about is, well, what's happening to the resistance of the circuit? Well, the resistance of the circuit is getting larger because every time that I add another resistor in the line, the total resistance of the circuit increases. So we're going to say for a series circuit, plus 3 plus ... plus Rn. Okay, that's my equation for finding the resistance of a series circuit. Now notice that's just the resistance of a series circuit. Well, why is that true? I can derive that from plugging this into this equation, these equations in this equation, and using the junction rule in order to do it, but we're not going to kind of go through that because whatever, we're getting close to the end here, folks. All right, so now let's talk about the other type of circuit. So how else could I have done this? Well, let me disconnect all these. Well, you might have said, well, hold on a second. Why can't I just, connect this to the battery and then separately and independently get another wire. So this wire is connected to the positive of the battery, boom, and then separately and independently connect the next one, to the battery. That's clipped to the terminal, and here we go. So each of them is independently connected to the battery, and well, there we go. Now, notice here, if I unscrew 3, 2 doesn't go out. If I unscrew 2, 3 doesn't go out, because these 2 pathways are independent. Now, someone is going to say, but Mr. Vaughn, I noticed that when I unscrewed 3, 2 got a little bit brighter. When I unscrewed 2, 3 got a bit brighter. And there's a reason for that, and that's because technically they are connected in some way because they're using the same battery, and there's wires inside the battery where they're sharing a pathway. So it's not a perfect version of this. So I'm admitting that up front. Surprise, batteries have resistances themselves. That's why batteries get hot over time when current goes through them. But anyway, we're going to pretend it's a perfect world. All right, so what's that type of resistor called? Well, that type of circuit is called a parallel circuit. And the notion of a parallel circuit is that there are multiple independent pathways. Okay, so therefore, each loop or path is independent of the others. Okay, so how am I going to draw that? There's a bunch of ways to draw that. I'm going to show 2 common ways of drawing that. So here, this one, right, just literally drawing 2 separate circuits that are just happen to be using the same battery. I'll call this R1, this R2, which would mean I would need to draw separate currents, I1 and I2. It's not actually commonly how we do that. Here's how we commonly would draw that. We would draw something that would look like this instead. Okay. And this, as long as my wires have no resistance, in theory, is identical to what I just drew. So where would the R1 and R2 be? Here, or their I1 and I2 would be here and here. But then I would have IT. I can see IT there. The benefit of this way of doing it is it really brings into home the theoretical concern that the pathways are independent. But the problem is, at some point there is a current through the battery, and this doesn't really show that well. But here it shows it quite well because it looks like there's a single path into the battery there. And this is actually how we tend to draw them, but this is conceptually better. So let's talk about the implications here. So we started before with the junction rule with the series circuit. I'm going to start with the loop rule for the parallel circuit. So if I think about one electron going around, because per loop, the amount of potential gain is equal to the potential dropped. But here's the thing, I have multiple loops now. Any given electron can only go along one loop, right? They take one path. And so here, an electron would go through the battery, get to this point, and either go down this way or this way. Now, it doesn't choose. You got to remember, there are literally moles of electrons flowing along, and just they distribute themselves across the two paths. We'll talk about how later. So, picks up energy, and then a given electron is going to go down either path. But notice, how many resistors does that electron visit? Just the one. And so therefore, by the loop rule, it's got to drop off all of its energy there, right? So whether it goes to 1 or to 2, it drops off all of its energy. So what we say is 2 branches in parallel, which is what these are, get the same voltage. So 2 branches in parallel get the same voltage. 2 resistors in series get the same current. 2 branches in parallel get the same voltage. And notice I'm not saying 2 resistors in parallel, because we talk about these things as branches in a pathway, right? Because technically, as things get more complicated, if I have 3 resistors, I might have 2 resistors on this branch. But we're not going to do that. I'm just talking about why I'm using the word branch there. Now, Kirchhoff's junction rule. Why do I keep saying junction? Oh, well, now we see it, because that's a junction, folks, as is that, right? Anywhere where there's a split in path, that is called a junction. So those 2 dots are junctions. So what does the junction rule say? Well, it says the current into a junction, or any current element, circuit element, is equal to the current out. So here, notice what do I have going in? IT. What do I have coming out? I1 and I2. So therefore, IT is equal to I1 plus I2. Now, coming down here at the bottom, what's coming in? I1 and I2. What's going out? IT. It's just that simple. So I1 plus I2 equals IT. Now, these 2 statements are mathematically equivalent, but I think conceptually they say 2 very different things. The first one says that the current through the battery gets split up amongst the branches. And the second one says the current of the branches come together to make IT. One of those statements is true, and one of those statements is false. And this is very subtle, but very important. So, here's the thing. If I were to add another branch in parallel, so here, let's just draw the first 2. And I'll do it in this way because I think it helps conceptually, right? I think you would agree that the current through the battery would be the current that's going through this branch plus the current's going through this branch. Remember, parallel, they're completely independent. Therefore, if I add a third branch, what happens to the current through the first branch? Well, hopefully you said nothing, because the branches are independent of one another. What ends up happening is I get another grouping of wires subjected to an electric field, which causes an additional amount of current to flow. So instead of thinking of like it's a current through the battery that gets split amongst the branches, I want you to think about it as it's the current through the branches that add together to make the main current. because when I add resistors in parallel, what ends up happening is that more total current flows, right? So that's important. IT actually increases when I have when I have more resistors in parallel. Well, hold on a second, that's weird. If IT increased and delta VT stayed the same, well, by Ohm's law, well, what must be happening over there? Well, if that increases, that must decrease. Oddly enough, adding resistors in parallel decreases the effective resistance in the circuit. And you might be looking over here and saying, but that doesn't work because of this equation. But this equation is only true for series, folks. In parallel, the equation is actually the following. Is that in parallel, the effective resistance is actually the inverse of the effective resistance is the sum of the inverse of all the branch resistances. So sort of a weird thing there. So in parallel, that's what's going on. Now, these currents might not be equal either because they're totally independent of each other. How do I know how much current any given branch gets? Well, that's going to be using Ohm's law. Delta V1 over R1. I2 is delta V2 over R2. In this case, I3 would be delta V3 over R3. And hopefully you're saying to yourself, oh, in parallel, everyone gets the same voltage because branches get the same voltage. And therefore, if you notice here, then the branch with the lowest resistance gets the highest current. Oh, that makes sense because the path of least resistance gets the most current. That should make sense to you. And that's proven out in the math here. So if I had 3 resistors that were equal, each of these branches would have the same current going down them. But if these had 3 different resistances, there would be 3 different currents adding up to get to the total current. And the branch with the least resistance would have the most current, right? And so in the last video, what you'll look at is an application of danger points. And mostly danger points happen here because hopefully what you notice is in a parallel circuit, we're going to have higher total currents flowing. And that means that there's a large draw on the voltage source and it runs out of energy a lot quicker, but also these wires are going to heat up because there's more current going through them, right? And so that'll bring it together. Theoretically, we would have done problems with all of these equations, but I just wanted to kind of go through this conceptual thing. So just to bring it all together. In series, all the resistors are dependent upon each other. They split voltage. They each get the same current. The more resistors you have in series, the larger the total resistance, the less voltage each gets, and the smaller the total current is. In parallel, each branch is independent. Each branch gets the same voltage, which is the same as the source voltage. The currents are independent of each other. Different resistors will get different amounts of current, but the same amount of voltage. The lowest resistance gets the most current, and those currents add up together to make the total current that flows through the battery. Therefore, more branches means larger total current, so therefore, lower total resistance. And that is the basic idea of circuits with multiple resistors.